After Newton, astronomical advances in observation and theory were at first slow. Better telescopes had yet to be developed, photography and spectroscopy were introduced into astronomy, and the chemical compositions and radial velocities of stars and nebulae were determined. The puzzling nature of the nebulae had yet to be resolved. Nebulae in the galaxy to be distinguished from extragalactic nebulae, distance indicators to be found and calibrated, globular clusters to be identified as systems of stars lying in and on the outskirts of the galaxy, and the confusing obscuration of starlight caused by interstellar absorption to be recognized. All this would be accomplished and accompanied by the continual debate over controversial issues from Newton to the time of Einstein, during the 18th, 19th, and early 20th centuries. Hierarchical universes. Those who live in deserts, sail the seas, or live in out-of-the-way places far from city lights understand why the night sky was so significant to people of earlier times. On clear, moonless nights, the vault of heaven swarms with dazzling stars and nebulous lights. And the Milky Way, the Via Lactea, arches wraith-like across the sky. At the beginning of the 18th century, the centerless and edgeless Cartesian and Newtonian systems were uniformly strewn with stars. But as astronomers widened their horizons and developed better telescopes, it became increasingly difficult to ignore the obvious truth that stars are not scattered uniformly across the sky. In the north of England, Thomas Wright of Durham had novel ideas concerning the Milky Way that he presented in his book, An Original Theory of the Universe, published in 1750. At first, he said, he had supposed that the stars were promiscuously distributed through the mundane space. But later, because of the Milky Way, he realized that the stars were scattered in some regular order. A feature of Wright's universe was the existence of a supernatural galactic center. At this center of creation, he would willingly introduce a primitive fountain, perpetually overflowing with divine grace, from whence all the laws of nature have their origin. He proposed two possible constructions of the Milky Way system: either a ring-shaped distribution of stars encircling the center of the Milky Way, similar to the rings encircling Saturn, or a spherical shell of stars, concentric with the center, in which the Milky Way consists of the stars seen in a plane tangential to the shell. Wright went further and speculated on the possibility of many centers of creation. The distant nebulae, seen as faint and fuzzy lights in the sky, are perhaps other creations or abodes of the blessed, similar to our Milky Way. The endless immensity is an unlimited plenum of creations not unlike the known universe. Kant, a German philosopher and scientist, saw a review of Wright's work and adopted the idea that the Milky Way is a disc-shaped or lens-shaped distribution of stars, and the Milky Way is surrounded by distant, similar Milky Way systems. In his theory of the heavens, Kant presented 1755 a scientific account of Wright's views. The stars of the Milky Way form a rotating disk held together by gravity, said Kant, and the fuzzy nebulae are similar rotating Milky Way systems. It is natural to assume that these nebulae are systems of numerous suns, which appear, because of their stance, crowded into a space so limited as to give a pale and uniform light. Their analogy with our own system of stars, their shape, which is just what it should be according to our theory, and the faintness of their light, which denotes great distances, are in admirable agreement, and lead us to consider these elliptical spots as systems of the same order as our own. Kant said these Milky Ways, now called galaxies, are perhaps clustered, forming vast systems of many galaxies. He conjectures that these vast systems are clustered together to form even vaster systems, which are clustered together to form yet vaster systems, and so on, throughout infinite space. Figure 4.5. In such a cosmic hierarchy, each level consists of an infinite array of centers, and the centers at each level form clusters about the centers of the next higher level. At the highest level of infinite order, the ultimate center dominated the universe's structure. We see the first members of a progressive relationship of worlds and systems, and the first part of this infinite progression enables us to recognize what must be conjectured of the whole. There is no end here but an abyss of a real immensity, in which all the capability of human conception sinks exhausted. Johann Lambert, a Swiss-German mathematician, entertained similar ideas. The main difference was Lambert's assumption that each center was occupied by a body that he called dark regent. In Cosmological Letters, Lambert wrote in 1761, "The eye, assisted by the telescope, may at length penetrate all the way to the centers of the Milky Ways, and why not even to the center of the universe?" Von Humboldt, a restless man with broad scientific interests, introduced the term cosmical island, 1855, in his book Cosmos, when he wrote, "Our cosmical island forms a lens-shaped system of stars." Authors soon popularized cosmical islands as island universes and island universes. Unfortunately, confusion creeps in when galaxies are referred to as universes. We shall instead refer to galaxies as islands. Thus, a Stoic-like system is a one-island universe, and an Epicurean-like system is a many-island universe. When the arrangement in a hierarchy repeats itself on several levels, the hierarchy is known as a fractal, a term introduced by the French scientist Benoit Mandelbrot. For example, the irregularities of a coastline, seen on a scale of tens of meters, then kilometers, and then hundreds of kilometers, may look much the same. Kant's hierarchy possessed fractal properties. Stars form clusters, each of n1 stars, at the first level. Star clusters form galaxies, each of n2 star clusters, at the second level. Galaxies form galaxy clusters, each of n3 galaxies, at the third level. Galaxy clusters form superclusters, each of n4 galaxy clusters, at the fourth level, and so on. The Nebular Hypothesis. Pierre Simon de Laplace, 1749 to 1827. Laplace, a French mathematician and astronomer, demonstrated in his Celestial Mechanics the stability of the planetary system, and thereby dispensed with periodic corrections by a divine power that Newton had invoked. In his non-mathematical and popular System of the World, first published in 1796, Laplace discussed the hypothesis that the solar system had formed from a rotating and contracting gas cloud. According to this idea, now accepted in modernized form, the Sun and planets originally condensed from a large swirling cloud of interstellar gas. Possibly other solar systems had formed similarly. In his book The Theory of the Heavens, Kant advanced the same idea earlier, but with less emphasis on the importance of rotation. The Kant-Laplacian Nebular Hypothesis. Nebula, which means cloud, caught the imagination of astronomers and natural philosophers. In the 19th century, every fuzzy patch of light in the night sky became a possible interstellar cloud of condensing gas. Even the Andromeda Nebula, a giant neighboring galaxy, and similar nebulae became conjectural solar systems in the formation process. Cosmical islands, the distant nebulae. The small, faint and fuzzy patches of light and the density decrease with size as L to the power of -1 equals 11. Fractals are discussed further in chapter 24. Suppose that 1,000 galaxies, each of size 1, in the night sky, figure 4.8, according to the right Kantian interpretation, were distant Milky Way systems of stars, and, according to the Kant-Laplacian interpretation, were clouds of gas condensing into solar systems. The Milky Way interpretation favored a many-island universe, whereas the solar system interpretation favored a one-island universe. These opposing interpretations took center stage in a melodrama lasting until the early 20th century, in which astronomers seesawed from one interpretation to the other. William Herschel, 1738 to 1822. Herschel, a professional musician born in Germany, emigrated to England at age 19. Later, his sister Caroline joined him, and they became ardently interested in astronomy. Using state-of-the-art telescopes they made, they resolved many nebulae into clusters of stars. Following his sensational discovery of a seventh planet beyond Saturn, later named Uranus, William became famous and was recognized as the leading astronomer of the 18th century. The Herschels surveyed the heavens with telescopes of unrivaled precision and light-gathering power. In publications, William interpreted their results based on three assumptions. I. Interstellar space is transparent to starlight. All stars are similar to the Sun. Stars are distributed uniformly in space. All three were later found to be in error. The first and second assumptions meant the faintest stars were the farthest, and apparent brightness could be used as a distance measure. The first and third assumptions meant the Milky Way extended the farthest, where the sky appeared the most crowded with stars. Based on these assumptions, the Herschels charted the heavens and found the Milky Way to be a flattened system, as shown in Figure 4.9, with the Sun positioned near the center. The galactocentric theory, that the Sun is at the galaxy's center, was primarily the consequence of assumption I. No astronomer at the time knew of the pronounced absorption of starlight caused by clouds of dusty gas drifting between the stars. The center of the galaxy is the constellation of Sagittarius, which hides the galaxy from view. William believed that the starless regions of the sky, now known to be caused by obscuring clouds of gas and dust, were holes in the sky, through which we see the darkness beyond the Milky Way. The Herschels showed that the motions of double stars, two stars in orbit about each other, align with Kepler's laws. In 1785, inspired by the Wright-Kantian hypothesis, William wrote in a paper entitled On the Construction of the Heavens that many nebulae may be very distant systems similar to our Milky Way, for which reason they may also be called Milky Ways by way of distinction. In a letter he wrote, he had discovered 1,500 universes, whole sidereal systems, some of which might well outvie our Milky Way in grandeur. For most of his life, he supported the view that the universe is endlessly populated with galaxies, much like the Milky Way. But the riddle of the nebulae grew more puzzling, and with the rise in popularity of the Kant-Laplacian nebula hypothesis, William grew less confident, and eventually expressed the opinion that possibly most nebulae existed inside the Milky Way. His observations of double stars made him realize that stars in general can be greatly different in brightness, and the second assumption, all stars are alike, was untenable. So was the third assumption. Stars are uniformly distributed in space. And he realized that stars are scattered with pronounced irregularity. Some nebulous regions, as in Orion, looked like a shining fluid and not like a collection of stars, thus raising doubts concerning the first assumption. William Herschel believed that the moon and planets were inhabited by living creatures. It seems astonishing, however, that the foremost astronomer in the Age of Reason could believe that a cool surface, also inhabited by living creatures, existed beneath the bright atmosphere of the Sun. But this was before the marriage of physics and astronomy and the birth of the new astronomy. The new astronomy. The speed of light. Reason assured Descartes that light travels at infinite speed and we see the world as it is. How confused would our reconstruction of the external world be if the light rays composing an image coming from different distances originated at different times? A finite speed meant that an object at the moment of observation was not what it seemed. It had moved elsewhere and changed its appearance. Objects at greater or lesser distances would have moved and changed by greater or lesser amounts. The idea that when we look out into space we look back in time seemed to Descartes and many Cartesians too incredible to be taken seriously. But in 1676, the Danish astronomer Ole Rømer announced at the Paris Academy of Sciences meeting that the eclipse of Io, a moon of Jupiter, on November 9th would occur 10 minutes late. His prediction was based on earlier records. Romer explained that the Earth was moving away from Jupiter, and the delay would be caused by the extra distance that light had to travel to catch up with the Earth. This correct prediction established him as the discoverer of the finite speed of light. The results, updated by Edmund Halley, showed that light travels at the enormous speed of 300,000 kilometers a second and takes only 500 seconds to travel a Sun-Earth distance, known as an astronomical unit. Noting that parallax of the stars caused by the Earth's orbit about the Sun had not been detected and that stars were therefore farther away than a certain minimum distance, Francis Roberts in 1694, in a paper concerning the distance of the fixed stars, reckoned that light takes up more time travelling from the stars to us than we in making a West India voyage, which is ordinarily performed in 6 weeks. Light travel time is important in cosmology, and this was its first use as a distance measure. But the parallax of even the nearest stars is far less than Roberts imagined, and their light takes years, not weeks, to reach us. Opposition to the finite speed of light ended in 1729, when James Bradley discovered the aberration of light. He observed that stars move backward and forward by a small angle during the year, because of the Earth's motion around the Sun. And the angular displacement, independent of the distance of stars, unlike parallax, was in agreement with Romer's finite speed of light. When a person walks in vertically falling rain, the rain slants towards the person's face, and an umbrella is tilted forward. The slant of the rain is analogous to the aberration of light. In her System of the Stars, 1890, Agnes Clerk, a leading 19th century historian of astronomy, wrote, "For our view of sidereal objects is not simultaneous. Communication with them using light takes time and postdates the sensible impressions of their whereabouts in direct proportion to their distances. We see the stars not where they are, not even where they were at any one instant, but on a sliding scale of instants. A fact of paramount importance in cosmology is that when we look out in space, we also look back in time. And the farther we look out in space, the farther we look back in time." Rays of light. Although Newton spoke of ether waves that vibrate like sound waves, or are like the waves on the water's surface, he nonetheless believed that light is composed of particles and asked, "Are not the rays of light very small bodies emitted from shining bodies?" Robert Hooke and Christian Huygens proposed wave theories of light that explained reflection and refraction, bending of light as in a prism. A century later, in the early years of the 19th century, Thomas Young, a physician, scientist, and authority on Egyptian hieroglyphics, showed how the wave theory explained interference. Superposed waves of the same wavelength add and subtract, and diffraction, deflection, according to the wavelength of waves passing through an aperture. In the middle decades of the century, Michael Faraday, an outstanding experimental physicist, and James Clerk Maxwell, an outstanding theoretical physicist, explored and unified electricity, magnetism, and the properties of light, and developed the modern theory of electromagnetism. Early in the 20th century, Max Planck and Albert Einstein showed that light has wave-like and corpuscular properties, and radiation particles are now called photons. William Huggins, 1824 to 1910. The new astronomy of the 19th century, later known as astrophysics, began when astronomers sought the aid of physics in studying stars and nebulae. Literally, the laboratory moved into the observatory, figure 4.10. A major contributor to the new science was William Huggins, who pioneered the application of the new technologies of photography and spectroscopy to astronomy, and was later greatly aided by his wife, Margaret. Spectroscopic analysis of sunlight had already shown that the sun consisted of the same elements as the Earth, and Huggins resolved to do the same for the stars. A principal problem in astronomy throughout most of the 19th century concerned the nature of the nebulae, the fuzzy patches of light in the night sky. Three possibilities confronted astronomers. The nebulae were: A. Distant galaxies like our galaxy. B. Clouds of swirling gas condensing into stars and planets. C. Clusters of unresolved stars in and on the outskirts of the galaxy. The first possibility, A, was the Wright-Kantian many-island universe, now less popular after losing the support of William Herschel. The second possibility, B, was the Kant-Laplacian nebula hypothesis, now gaining in popularity. The third was that many nebulae were clusters of hitherto unresolved stars, a possibility of growing popularity due to the discoveries made by greatly improved telescopes. Possibilities B and C were consistent with a one-island universe. A light spectrum from a luminous source shows how the intensity varies with wavelength. A spectrum often displays bright and dark narrow regions called spectral lines. These are the emission, bright, and absorption, dark, lines at different wavelengths that identify the emitting and absorbing atomic elements. Working in his home observatory, Huggins compared the spectra of light from stars, nebulae, and comets with the spectra of elements excited in spark gap discharges. Notice the battery, wires, and induction coil in Figure 4.10. In 1863, Huggins finally succeeded and announced to the scientific world the news: the heavens are composed of the same elements as the sun and earth. This was the death blow to many old beliefs, and ordinary people began to turn from the churches to the observatories for knowledge on the nature of the starry heavens. A year later, in 1864, William Huggins wrote, "I directed the telescope for the first time to a planetary nebula in Draco, and with hesitation, put my eye to the spectroscope. Was I not about to look into a secret place of creation? What he saw was not what he expected. The spectroscope showed not the continuous spectrum characteristic of a hot star, but a spectrum of lines characteristic of an excited gas. The riddle of the nebulae was solved. The answer, which came to us in the light itself, read, 'Not an aggregation of stars, but a luminous gas.' This discovery swept away all doubts about the truth of the Kant-Laplacian nebula hypothesis. The puzzling elliptical and spiral nebulae were not clusters of suns, as many had previously supposed, but gaseous nebulae that, by their gradual heat loss, were contracting to form solar systems. Thus, assumption A, Doppler effect. Huggins was also the first to measure the radial velocity, the velocity away from and toward us, of stars by observing the shift in their spectral lines. This shift, now known as the Doppler effect, was predicted and calculated in 1848 by the French scientist Armand Fizeau. Fizeau, in 1849, was also the first person to measure the speed of light by terrestrial methods. When a luminous source, such as a candle or a star, moves away from an observer, all wavelengths of its radiation are increased, and all frequencies are decreased. And when the source moves toward the observer, all wavelengths are decreased, and all frequencies are increased as seen by the observer. To a swimmer striking out from the shore, each wave is shorter, and the number of waves he goes through in a given time is greater than would be the case if he stood still in the water, wrote Huggins in The New Astronomy, a personal retrospect. Christian Doppler, an Austrian physicist, showed in 1842 that a receding or approaching sound source is heard with a lower or higher pitch than when stationary. In 1848, he suggested that stars have different colors because of their motions, and that stars in binary systems periodically change their color, becoming blue when approaching and red when receding. Fizeau made the correct calculation and showed this was not the case. The displacement of spectral lines caused by relative motion was known in the 19th century as the Fizeau-Doppler effect, and today, perhaps less justly, as the Doppler effect. Detection of the effect was difficult until photography advanced to the stage where dry and sensitive plates could be exposed for hours in clock-driven telescopes. William Huggins prophetically wrote of the Fizeau-Doppler effect in 1868 that it would be scarcely possible to sketch, even in broad outline, the many glorious achievements that doubtless lie before this method of research in the immediate future. A working atomic theory. The modern atomic theory of matter began in 1803 with John Dalton's book New System of Chemical Philosophy, which became an immediate success. Dalton introduced the Greek word atom into chemistry, and was the first scientist to make the atomic theory quantitative. Because elements combine in definite proportions by weight to form chemical compounds, he showed that matter comprises atoms of different weights. Hydrogen was said to have an atomic weight of 1. On this scale, carbon had an atomic weight of 12, oxygen 16, and so on. Joseph Thomson discovered the negatively charged electron in 1897. Ernest Rutherford discovered the positively charged atomic nucleus in 1911. Niels Bohr constructed in 1913 a mechanical model of the atom with electrons in orbits about the nucleus. And a few years later, Erwin Schrödinger, Werner Heisenberg, and other physicists developed the modern wave mechanical model of the atom using quantum mechanics. When it comes to atoms, said Bohr, language can be used only as in poetry. The Victorian universe. The standard cosmological model of the 19th century. The Victorian universe was the standard model of the 19th century during the reign, 1837 to 1901, of Queen Victoria of Great Britain. Propelled by the rise of new astronomy, it reached its final form toward the end of the century. It was a one-island universe. Providentially, the Earth and Sun were located at the center of the galaxy, the universe's mainland, surrounded by small islands. The galaxy, figure 4.12, consisted of approximately 1 billion stars. Numerous clusters of stars, often unresolved and on the outskirts, and gaseous nebulae, mostly condensing solar systems and planetary nebulae. And beyond the galaxy stretched an endless, mysterious void more fit for contemplation by theology gains than astronomers. The many wonders of the Victorian universe, glorified in hundreds of popular astronomy books and proclaimed from every pulpit, thrilled a large audience in Europe and North America. Agnes Clerk, the leading late 19th century historian of astronomy, summed up the consensus view in 1890 in her book, The System of the Stars. Some nebulae, she wrote, were clouds of swirling gas, and some were clusters of unresolved stars, but none were galaxies like our own Milky Way. No competent thinker with all of the available evidence before him can now, it is safe to say, maintain any single nebula as a star system of coordinate rank with the Milky Way. A practical certainty has been attained that the entire contents, stellar and nebular, of the sphere belong to one mighty aggregation and stand in ordered mutual relations within the limits of one all-embracing scheme. All-embracing, that is to say, so far as our capacities of knowledge extend. With the infinite possibilities beyond, science has no concern. This, more or less, was the standard model of the Victorian universe, inherited by the 20th century. In some respects, the Victorian universe was the old Stoic one-island universe. Updated and refurbished with stars, planets and gaseous nebulae made of atoms similar to the solar system. The Stoic solution of the dark night sky riddle lent further support to a one-island universe. Clarke wrote, "The probability amounts to a certainty that the stellar system is of measurable dimensions. Otherwise, darkness would be banished from our skies, and the intense inane glowing with the mingled beams of suns, individually indistinguishable, would bewilder our feeble senses with its monotonous splendor. In an infinite universe endlessly populated with stars, every line of sight from the eye, extended out in space, must ultimately intersect the surface of a star. Stars must cover the entire sky. Hence, The riddle is Olbers's paradox. Why is the sky dark at night? However, the finite cosmos of stars discussed by Clerk is only one of several possible solutions, not accepted 100 years later. The age problem. Until the 18th century, Jews, Christians, and Muslims believed the universe was only thousands of years old. Mounting evidence in geology and paleontology, the study of fossils, indicated a much greater age and brought scriptural records into conflict with science. Doctrines of compromise were developed in which the Earth had been periodically visited by catastrophes, such as life-destroying deluges, and supernatural and natural laws had alternated in their control of the Earth. Far away and long ago. For more than 200 years after Romer's discovery, astronomers tended to ignore the significance of the finite speed of light concerning the universe's age. There were a few exceptions. William Herschel, bolder than most, occasionally remarked that we see the heavens as they were long ago. In 1702 he wrote, "A telescope with a power of penetrating into space. Like my 40-foot one," see figure 4.7, has also, as it may be called, a power of penetrating into time past. In fact, the light rays from a certain very remote nebula must have been almost 2 million years on their way. And consequently, so many years ago, this object must already have had an existence in the sidereal heavens to send out those rays by which we now perceive it. William Herschel's son John, a more cautious man, wrote in 1830 in a treatise of astronomy, "Among the countless multitude of such stars visible in telescopes, there must be many whose light has taken at least 1,000 years to reach us, and that when we observe their places and note their changes, we are, in fact, reading only their history of 1,000 years anterior date, wonderfully recorded." John Herschel, a pillar of Victorian society, was not a Don Quixote to sally forth and tilt at solidly held religious beliefs concerning the universe's age. But not von Humboldt, who wrote in his book Cosmos, "It still remains more than probable from the knowledge that we possess of the velocity of transmission of luminous rays, that the light of remote heavenly bodies presents us with the most ancient perceptible evidence of the existence of matter." The fundamental fact that when we look out into space, we also look back in time to the beginning, was not openly explored in the Victorian universe. Lord Kelvin, in 1901, coincidentally, the year that Queen Victoria died, performed what no astronomer had dared. In the article On Ether and Gravitational Matter Through Infinite Space, he made the relevant calculations on the connection between the age of the oldest luminous stars and the age and extent of the visible universe. However, evidence from the heavens of the cosmic age came too late. The cosmochronology of Genesis had already been controverted by geologists who showed that the universe's age must be measured not in thousands, but in millions, and perhaps even billions of years. Geology. James Hutton, a Scottish farmer and physician, proposed in 1785 that the formation and erosion of mountains are continuous processes that have acted over an indefinite period. From the evidence, he found no vestige of a beginning, no prospect of an end. This was the beginning of the steady-state uniformitarian principle, powerfully argued by Charles Lyell. The landscape is continually modified by mountain uplift, erosion, and sedimentation, and the surface remains unchanged. Into this picture of an Earth of great, if not unlimited age, fitted Charles Darwin's theory of evolution, presented in 1859 in his book On the Origin of Species by Natural Selection. On the one hand, the catastrophists believe in a world periodically visited by catastrophes, and the uniformitarians, on the other hand, believe in a steady-state world controlled by natural laws. The controversy between the two schools until the end of the 19th century was far more heated than the controversy between the Big Bang and steady-state schools of the 20th century. In the second half of the 19th century, the uniformitarians were attacked by physicists under the leadership of Lord Kelvin. Calculations, now known to be inapplicable, on tidal effects and terrestrial heat losses showed the Earth could not be as old as the geologists claimed. The calculated age of the Sun was the most decisive. Kelvin adopted Hermann von Helmholtz's idea that gravitational energy released by the slow contraction of the Sun fueled the Sun's luminosity. He estimated the age of the Sun as 20 million years. See Chapter 5. Because a luminous Sun is essential for life on Earth, this implied that fossils could not be older than 20 million years. The insistence by the physicists during this short period created dismay in the Earth and life sciences, and attempts were made to fit geological history and the evolution of life into Kelvin's short chronology. In the early 20th century, physicists redeemed themselves with radioactive dating methods and showed that the Earth's age is measured in billions, not millions of years. Ernest Rutherford, in his book Radiation and Emanation of Radium, 1904, wrote, "The discovery of the radioactive elements, which in their disintegration liberate enormous amounts of energy, thus increases the possible limit of the duration of life on this planet, and allows the time claimed by the geologist and biologist for the purpose of evolution." Fall of the Victorian universe. The long competition between the Stoic and Epicurean systems and their popularity alternating, lasting for over 2,000 years, ended in the early 20th century. In the late Middle Ages, the finite medieval universe of celestial and angelic spheres evolved into a Stoic system of celestial spheres, immersed in an infinite and mysterious void. Then the awesome poem De Rerum Natura, discovered in 1427, burst on the scene, opening the minds of Western Europeans to the dizzy prospect of a vast Epicurean system. Nicholas of Cusa, Thomas Diggers, Giordano Bruno, William Gilbert, and numerous natural philosophers, Cartesian and Newtonian, spread the message. But in the 18th century, the evidence was confusing. The pendulum eventually swung again in the 19th century, and the standard model of the universe was a one-island Stoic system. In the early decades of the 20th century, the old debate once more flared up. Are we the inhabitants of a one-island or a many-island universe? Harlow Shapley, 1885 to 1972, an American astronomer studying the distribution of globular clusters, compact clusters of very old stars, 1918 overthrew the Herschel galactocentric system. He found that these clusters form a spherical distribution whose center lies tens of thousands of light-years away in the direction of the constellation Sagittarius. A light-year is the distance light travels in 1 year and equals 63,000 astronomical units. The globular clusters. Shapley observed that the globular cluster belongs to our galaxy, suggesting that the galaxy's center is also the center of their distribution. Jan Oort, a Dutch scientist, confirmed this result. Astronomers confirmed this result by showing that the stars of the Milky Way are orbiting about the distant center. In the early 1920s, Shapley championed the one-island universe, and Heber Curtis, another American astronomer, championed the many-island universe. Because of insufficient allowance for absorption of starlight by interstellar dust, Shapley overestimated the distances of the globular clusters and made the galaxy much too large. Curtis underestimated the distances of the stars and made the galaxy much too small. The Victorian vision of a giant galaxy was defended by Shapley until 1930, and then finally abandoned. This tussle in ideas, referred to by some historians as the Great Debate, ended the long struggle between the rival Stoic and Epicurean systems. The controversy ended in favor of an Epicurean-like system originally conceived by the atomists of the ancient world. A puzzle remained. Our galaxy seemed much larger than other galaxies. Walter Baade solved the puzzle in 1952, distinguishing between population Poims and two stars, chapters 5 and 6, and between the Cepheid variables of these two stellar populations. This had the effect of doubling the distances and sizes of other galaxies, and the Milky Way no longer seemed disproportionately large. Reflections. 1. Immanuel Kant of Königsberg, scientist and philosopher, published A Deep Searching Philosophy, 1781, under critique of pure reason. According to Kant's philosophy, the world of sensations is organized into meaningful perceptions by an activity of a priori, subconscious, ideas of primitive origin. These primitive ideas, from all past experiences of the species, are essential for making sense of our fleeting and disjointed world of sensations. In Plato's philosophy, the ideas that organize our experiences belong to the universal mind. In Kant's philosophy, they belong to our own minds. 2. William Herschel said that astronomy has much in common with botany. In a paper, On the Construction of the Heavens, he wrote, "This method of viewing the heavens seems to throw them into a new kind of light. They are now seen to resemble a luxuriant garden, which contains the greatest variety of products, options in different flourishing beds. And one advantage we may at least reap from it is that we can, as it were, extend the range of our experience to an immense duration. For to continue the simile borrowed from the vegetable kingdom, is it not always the same thing whether we live successively to witness the germination, blooming, foliage, fecundity, fading, withering, and corruption of a plant, or whether a vast number of specimens, selected from every stage through which the plant passes in the course of its existence, be brought at once to our view? To learn how an oak tree grows, we do not study a single oak in isolation, growing over a long period, but many oaks in a forest in different stages of growth. Similarly, with stars." Richard Proctor, in Our Place Among the Infinities, 1876, wrote on William Herschel's change in cosmological ideas. As the work progressed, Sir William Herschel grew less confident. He began to recognize signs of a complexity of structure, which set his method of star gauging at defiance. It became more and more clear to him also, as he extended his survey, that the star depths were, in fact, unfathomable. 3. The compilation of catalogues stating positions, descriptions, and spectral compositions is the main aim of observational astronomy. Charles Messier, 1730 to 1817, a French astronomer and ardent comet hunter, compiled a catalogue of 103 nebulae. He did this so that astronomers would not confuse these same nebulae with comets just beginning to shine. The Messier nebulae are prefixed with the letter M. Thus, M1 is the Crab Nebula, described as whitish light and spreading like a flame, and M31 is the galaxy in Andromeda. William Herschel published catalogues listing positions and descriptions of thousands of nebulae. John Herschel continued this work and published the General Catalogue GC in 1864. This was the first systematic survey of the entire sky and contained 5,000 nebulae and star clusters. The GC was replaced in 1890 by the new General Catalogue, NGC, and subsequent supplements, index catalogues, were added. Thus, the galaxy M31 is also known as NG C224. We are told that Napoleon Bonaparte, Emperor of the French, said to Laplace concerning his celestial mechanics, "You have written this huge book on the system of the world without once mentioning the author of the universe." Laplace replied, "Sire, I had no need of that hypothesis." Whether true or not, this story illustrates the difference between theism and deism. Theism is the ancient belief that God created and ran the universe. Deism came in the Age of Reason and is the belief that God created a self-running universe. Newton was a theist, Laplace a deist. 5. Hierarchical astronomy became respect. Able to be a serious possibility when John Herschel and Richard Proctor introduced it as a solution to the riddle of darkness at night. This idea was adopted by the Irish physicist Fournier d'Albe in England and the Swedish astronomer Carl Charlier in the early 20th century. Charlier, whose work received wide publicity, showed that if the density of the clusters decreased sufficiently rapidly with increasing size, corresponding to a fractal dimension of 2 or less, stars do not cover the sky, and the sky at night is dark. Fournier d'Albe put forward the hierarchical idea that the visible universe is only one of a series of universes containing solar systems of increasing size, arranged such that the solar systems in one universe are the atoms in the next higher universe, and so on. He showed that in universes made this way, the sky at night is dark. The gathering of stars into galaxies, galaxies into clusters, and clusters into superclusters constitutes what astronomers often call a hierarchy. Strictly speaking, this is a misuse of the word. A hierarchy is a pecking order organization that usually, but not always, consists of human beings, in which each member bosses those below and obeys those above. Government agencies and large businesses are hierarchies. The medieval universe, with its angelology and demonology, was also hierarchical. The technically correct word for Kant's hierarchy is multi-level. A complete multi-level universe, an infinite number of levels in an infinite universe, according to Kant and Lambert, has an ultimate cosmic center at the highest level. This center, however, is at an infinite distance, and its reality is open to debate. Fournier d'Albe and Charlier showed that the total amount of matter in a multi-level universe is much less than in a uniform universe. The mass and volume of the clusters steadily increase at higher and higher levels, and for clusters to stay separated from one another, their volume must increase faster than their mass. The average density, mass divided by volume, steadily decreases on progressively larger scales. In an infinite multi-level universe, the density of matter averaged over an infinitely large scale is vanishingly small. The observed universe's clumpiness is best represented by a finite hierarchy, or a finite number of levels, consisting of stars, star clusters, galaxies, galaxy clusters, and superclusters. Although this is uncertain, the universe may be uniform on scales larger than superclusters. 6. Our knowledge of the heavens comes from studying whatever reaches Earth. In old astronomy, observations were optical with color descriptions. In the new astronomy, observations were optical with spectral decomposition. In modern astrophysics, observations include all electromagnetic radiation, radio, microwave, infrared, optical, ultraviolet, X-ray and gamma ray, particle radiation, cosmic rays and neutrinos, and meteorites. Before the new astronomy, everybody believed that the chemical composition of stars was forever unknown. Auguste Comte, French mathematician, philosopher, and humanist, expressed this belief in his Cours de philosophie positive, 1830 to 1842. Any research that cannot be reduced to actual visual observation is excluded where the stars are concerned. We can see the possibility of determining their forms, their distances, their magnitudes and their movements, but it is inconceivable that we should ever be able to study by any means whatsoever their chemical composition or mineralogical structure. 7. The observatory became a meeting place where terrestrial chemistry was brought into direct touch with celestial chemistry. William and Margaret Huggins, Atlas of Representative Stellar Spectra. An unsigned article in a magazine, Good Words, on how to make your own spectroscope launched Margaret Lindsay into the new science of spectroscopy. She was a keen photographer and also an observer of the heavens with instruments she made. By chance, she met the article's author, William Huggins, who was visiting her hometown, Dublin, to inspect his new telescope. which was manufactured by Howard Grubb. Spectroscopy sparked romance, and in 1875 they married. Working as a team, he with failing eyes and she keen-eyed, they made observations, using state-of-the-art photography and spectroscopy, that helped launch the new astrophysics science. Queen Victoria, in 1897, knighted William by conferring the Order of the Bath for the great contributions which, with his gifted wife, he has made to the new science of astrophysics. Harrison, Darkness at Night. 8. For a long time, the cosmic consequences of a finite speed of light received little attention. Occasionally, astronomers pointed out that light travels a finite distance in a finite period. One or two expressed wonder that we see astronomical bodies as they were thousands and millions of years ago. The implication that the universe is at least as old as the time taken by light to travel from its farthest visible regions was either overlooked or left aside in articles, books, and lectures, possibly because it ran counter to prevailing religious dogma. The embarrassing thought that when we look out in space to the limit of the visible universe, we see things as they were in the beginning when the universe was created rarely surfaced in pre-relativity Victorian days. Many astronomers in Britain were ordained members of the Church of England, and astronomy, the most socially respectable and religiously correct of the sciences, was in the business of revealing the works of God and not of contradicting scriptural records. In the clockwork universe, God appeared to be only the clockmaker, the being who had shaped the atomic parts, established the laws of their motion, set them to work, and then left them to run themselves. Thomas Kuhn, The Copernican Revolution, 1957. Consider, are you a theist or a deist? In other words, do you prefer a universe created and controlled by a divine power, or a created self-controlled clockwork universe? Draw a two-dimensional fractal showing 3 levels and calculate the fractal dimension d. What does d less than 2 mean? Make a do-it-yourself fractal. Construct a 3-dimensional, 3-level fractal from simple materials, e.g. toothpicks and small rubber balls, and calculate the fractal dimension. 100 galaxies, each of size 1, form a cluster of size 10. 100 clusters form a supercluster of size 100, and so on. What is the fractal dimension? Kant imagined a multi-level universe covering infinite space and having an infinite number of levels. He said such a universe has an ultimate center. But this is puzzling. Is a center possible?